Hi all, this is our fourth part of chapter 6, Kinetic and Equilibrium. In part 4, our topic is the equilibrium constant. The common ion effect. In a saturated solution of an ionic compound such as silver chloride, the silver and chlorine ions are in equilibrium with the solid silver chloride. If additional chlorine ion were added to the solution, perhaps by adding some NaCl, Le Chatelier's principle predicts that the system would shift to the left in order to remove some of the added chlorine ions. As a result, more silver chloride, which is a solid, would be produced. The shift is known as the common ion effect. In this example, the addition of the common ion chlorine decreased the solubility of silver chloride in water because fewer silver ions present in the saturated solution. Heterogeneous equilibrium. An equilibrium is called homogeneous if all the reactants and products are in a single or same phase. In a heterogeneous system, pure solids or liquids are present. A saturated solution is an example of a heterogeneous equilibrium system. For example, carbon reacts with oxygen and make carbon dioxide. In this equation, solid carbon is in equilibrium with gaseous oxygen and carbon dioxide in a sealed container. If we add more solid carbon to the system, it would not affect the equilibrium because equilibrium is affected by changes in concentration, and adding solid carbon does not change the concentration because solid does not occupy the entire container as the gases do. The concentration of the solid, which is really its density, remains constant. It is also true with a pure liquid if it was part of an equilibrium system. Equilibrium constant, KEQ. When a system reaches equilibrium, it is useful to know the relative amount of products and reactants. Certain reactions produce hardly any products, while other reactions have hardly any reactants remaining. The equilibrium constant KEQ provides us with this information. Defining KEQ for a simple system. For a simple system where A is a reactant and B is a product, the equilibrium constant expression is defined as below. KEQ is equal to the equilibrium concentration of the product B divided by the equilibrium concentration of the reactant A. If KEQ is greater than 1, there is more products than reactants. If KEQ is lesser than 1, there is more reactants than products. If KEQ is equal to 1, the amounts of products and reactants are equal. Defining KEQ for a complicated system. For more complicated reactions, the equilibrium constant is itself more complicated. The equilibrium system, like below, the equilibrium constant expression is defined as following. For complex reactions, we still divide the concentration of products by the concentration of reactants and raise the concentration to the power of its coefficient. Solubility product constant, which is represented by Ksp, is a special type of equilibrium constant that measures the concentration of ionic compounds in water. A compound with a small Ksp value is slightly soluble in water. For example, calcium sulfate, whose Ksp value is 9.1 into 10 power minus 6, is only very slightly soluble in water. The Ksp expression may be developed by considering the solution equilibrium of an ionic compound AB, where AB is the reactant and A plus ion plus B minus ion are the products. Since AB is present as a solid, it is absorbed into the equilibrium expression. So our definition would be KEQ multiplied by concentration of AB is equal to concentration of A plus ion multiplied by concentration of B minus ion. This expression indicates the reason for calling Ksp a solubility product. It is equal to the product of the ion concentrations in water. Functions of chemical equilibrium. The Haber process. We have learned that ammonia is produced commercially by the reaction N2 plus 3H2 is equal to 2NH3 plus heat. And the formation of ammonia is favored by low temperatures and high pressure. The problem of using low temperature is that the rate of formation of ammonia is low. If the temperature is raised, however, the reaction is shifted to the left, which is endothermic reaction, thereby decreasing the yield of ammonia. In practice, an intermediate temperature, which is 500 degrees Celsius, is used as a compromise with a pressure of 200 to 1000 atmospheres and the addition of a catalyst. a reasonable rate of ammonia formation is maintained. Another example of applications of chemical equilibrium is the contact process. Sulfuric acid is one of the world's most important substances. It is produced by a four-step method known as the contact process. In first step, sulfur is burned to form sulfur dioxide gas. Then the sulfur dioxide is oxidized to form sulfur trioxide gas. This sulfur trioxide dissolves readily in concentrated sulfuric acid to form fuming sulfuric acid. The fuming sulfuric acid is dissolved in water to produce more sulfuric acid. The net reaction is as follows. SO3, which is gas, plus H2O, which is liquid, made H2SO4, which is liquid. The sulfur trioxide must be dissolved in sulfuric acid because it does not dissolve well in water. The formation of sulfur trioxide is just like formation of ammonia is favored by high pressure and low temperature. As with the Haber process, a compromised temperature which is 450 to 575 degrees Celsius is used along with a catalyst to maintain reasonable formation rate.